to the 2010 Birch lecture, which we will get to as quickly as we can here. But before we do, I'd like to make an award of the Tectonophysics Early Career Award, which is now named after Jason Morgan. And I want to award it to John Hernland of UC Berkeley. If John will come up. Where'd you go, John?
Right here.
Oh, there you are. Okay. So I'm very pleased to present you with this award. Congratulations.
Thank you very much, sir.
And we wish you a great career.
Thank you.
Okay, so we'll now move on to the Birch lecture, which will be given this year by Wang-Ping Chen of the University of Illinois. And so since we're running late already, I'll skip any other introductions. I'll give Wang-Ping his certificate and we'll get started.
Thank you very much. Thank you very much, Harry, and indeed it's my great pleasure and distinct honor to have this opportunity to speak to you in this special occasion. Francis Birch needs no introduction, nor does his landmark paper in 1952. I was required to read this paper when I was a senior in college, and it blew me away. Little did I know that I would actually have the opportunity to meet Francis Birch in person in a few years. Anyway, one point did stick with me, that it is the paradigm that Birch put forth in this paper, namely that in order to do a good job in understanding the interior of the Earth and other planets, we need to have a synergy between seismology and rock physics. Now, 15 years after Birch published this paper, there was another very important discovery, namely that the transition zone between the upper mantle and the lower mantle is indeed bound by two sharp seismic discontinuities at depth of 410 and 660 kilometers approximately. This discovery did not get too much press because at that time plate tectonics was really going strong. But in the aftermath of plate tectonics, this is really important. In fact, following Birch's paradigm, once this discontinuity is linked with major phase changes, then we have a way of estimating the temperature in the mantle because pressure is easily estimated. Then if we know the phase diagram, we will know the temperature. Now we know that there are actually major contrasts across these discontinuities in both rheology and in density, which in turn have important ramifications for mantle dynamics and for chemical mixing. Now globally, the seismic properties of the transition zone turns out to be highly variable. There are these very broad anomalies of high PNS wave speeds near the bottom of the transition zone. But as soon as we go across the 660 discontinuity, say down here, those anomalies become diminished. In the transition zone, the amplitude of these anomalies can reach plus minus 3%, but in the top of the lower mantle, the maximum amplitude is about 0.5%. Now, if we look closely at these different seismic anomalies, turns out there is a confounding variety of them. Some of them show up in both P and S waves. They give consistent amplitudes. Some of them don't. Some of them are associated with very large earthquakes, up to magnitude 7.5 or so. Some of them are aseismic, no earthquake activity. Most of the anomalies are isotropic, but some of them are anisotropic. So are they all related? And if so, how? Another important problem is the origin of deep focus earthquakes. At great depths, say 650 kilometers, conventional brittle failure or stick slip simply couldn't happen. Back in 1947, the president of AGU, Adams, listed the origin of deep earthquakes as one of 6 grand challenges in geophysics. But at that time, people probably have not invented the phrase yet, so he simply said that there are some unsolved problems in geophysics. I would also like to say a few words about how water is recycled into the Earth's deep interior. The obvious pathway is subduction, but is it very effective? And are there any alternatives to bring water into the deep mantle? Overall, I'm going to make the case that tectonic pathways and the petrological effects associated with these pathways can tie all these seemingly different anomalies as well as these different issues together. My emphasis is going to be on petrologic effect. As such, we require high-resolution studies that are available only in selected regions. And I'm going to accentuate connections of results among different disciplines. Now, the fact that we have seismic discontinuities bound in the transition zone was established by the so-called triplication in travel time curves. And this is a travel time curve. Look at just this event, deep event, event 2, right above the 660 discontinuity distance on the horizontal axis and travel time on the vertical axis. Look at this set of 3 red rays going to the same station. The top ray is the familiar refraction. The bottom ray actually dives into the lower mantle and then refracts back up to the stations. Even though the bottom ray traveled a longer distance than, say, the top ray, it arrives at about the same time as the top ray because there is a major increase in seismic wave speeds. Then the middle ray is a wide-angle reflection of the top of the 660. So in terms of the travel time, at a given place, you will see 3 arrivals within a few seconds of each other. This was the principle that was used to establish the discontinuity, and I'm going to rely very heavily on the same set of principles in our studies. Now, if we have a very large discontinuity here, then this bow tie basically will cover a very wide range in space, and also you will see large separations in time. So the bow tie is big if the discontinuity is big. Now, conversely, if the discontinuity is very small, the bow tie is going to get smaller and smaller. So in the limiting case, the bow tie gets smaller and smaller with smaller and smaller discontinuity. What happens if there is no discontinuity? There's no bow tie. So if you see a smooth travel time curve, then there is no discontinuity there. So basically now, with good seismic data and techniques, we can match seismograms wiggle by wiggle. Now, one word about broadband seismology. If we make our observations over a broad range of frequencies, what that means is simply that we have very high resolution in time. This allows us to identify individual arrivals with quite a bit of confidence. So let's look at some real data. This is a bunch of seismograms covering a distance over 1,000 kilometers. We are sampling the transition zone under Tibet, and this is time, and the solid traces are the observed seismograms, and the dashed traces are synthetic seismograms. And I have put in those bow ties. This one is associated with 410. The other one is associated with 660 to guide you. Now here we blow up these seismograms, and you can see that the synthetic and the observed seismograms are matched wiggle by wiggle. This is the bow tie that's associated with this set of data over here. What we see is that the time separation between these 2 branches, marked B and D, are very small. And the distance over which we observe this discontinuity is also small. It's just a few hundred kilometers. That means that the 660 at this particular location is fairly small. That is, there is a high velocity anomaly in the bottom of the transition zone. Well, it would be fun to look at the kind of data that Lane Johnson had 40 years ago when he first discovered this discontinuity. He had the same idea, the bow ties, but this is the data that he had to work with. And now we have just much better data and over much broader bandwidth. So let's move on to the first field area or natural laboratory here. That's the Tonga subduction zone. The biggest issue here is really the imbalance in mass. Okay? This subduction zone is remarkable. 2/3 of the world's deep seismicity occurs here. The rate of subduction is over 200 millimeters per year, and this is determined by a lot of GPS data. The slab being subducted is very old. It's Mesozoic in age, over 100 million years old. All this slab goes down to the mantle. Basically, a piece of lithosphere sitting at the trench takes only about 3 million years for it to reach the bottom of the transition zone. Well, where did all this slab go? Look at the tomographic results. This is a well-known paper by Steve Grant and colleagues. At 800 kilometers, Tonga is here and here. Well, you don't see much anomaly. Even at 1350, you don't see much either. So where is the slab? Now, the strong anomaly here, this blue band over here and here, is the so-called Caribbean anomaly. Presumably, it's associated with the subduction of Pharaon plate, which has stopped about 25 million years ago. So something very intricate is going on in terms of the slab penetration into the lower mantle. Ocean-wide studies, you're looking at several different things here. In the background, the blue and the red are tomographic results. Those circles are hypocenters, and then you have these wiggles. These are underside reflections of the two discontinuities, and the cross-section is this one. Basically goes from east to west here. So we do see this broad high-velocity anomaly associated with those deep earthquakes, and already notice how these earthquakes sort of spread out by over 1,000 kilometers from the tip of the Volatiles zone. Now, we know the 410 is associated with the olivine-spinel transition, which is an exothermal transition. So when you pump cold material down, the 410 should be elevated if we are under chemical equilibrium. But if you look at the data carefully, there is certainly no indication of this elevation, and that is certainly very interesting. So now we look in detail of this Tonga subduction zone. This is just a map showing the location of this cross-section over here. And 0 is here, 750 kilometer depths over here. Now there are sort of three patches of things being plotted here. This is the familiar Waraji-Benioff zone with hypocenters and the beach balls showing the focal mechanisms. And in this case, we have the familiar down-dip compression. This is an equal area projection of the p-axis, the axis of maximum compression. Now, this is a vertical plane because we're looking at a cross-section. So you can see that the p-axis congregate near those poles, which form a line which is subparallel to the shape of this distribution of seismicity. Now, there's this thing called outboard earthquakes. There's kind of floating away from the Waraji-Benioff zone. They are plotted in dark color here. So their p-axis actually is somewhere here. They don't align with the classic pattern. Then there is this toe, this deflected part of the slab. The data here are not plotted in this diagram, but basically they don't have any pattern as well. This cross-section runs from here to here by about 1,000 kilometers because there's a wide distribution of these so-called outboard earthquakes. Again, they don't form any pattern in terms of their P or T axis. Now, this doesn't look much. The separation between the black and the gray is actually 50 to 75 kilometers. Now, in terms of the seismic structure, the biggest anomaly is actually in isotropy. Now, there are two types of seismic anisotropy. One is related to the direction of propagation, which we're not going to talk about. The other is related to the direction of polarization. For shear waves, there are two components. One is basically in the plane of the propagation. The other is perpendicular to the plane of the propagation. In general, in the mantle, there is very strong shear wave anisotropy or birefringence or splitting, but the source region is in the top of the upper mantle. It's very unusual to find any sign of anisotropy in the transition zone, and yet in the source region of the outboard earthquakes, we see large split time up to 3 seconds. This slide pretty much summarizes all the results in the Tonga, Fiji region. The black dots are the outboard earthquakes, and they are actually now up to 12 stations, the French Cavascope broadband seismic array over here. And so there are so many deep focus earthquakes. We can perform a lot of different seismic profiles running from north, east-west, but then progress north to south. So we simplified the result and divide the area into 3 regions. This region 1 is where the outboard earthquakes are. Region 2 is immediately to the south of the outboard earthquake. Then region 3 is farther removed. If you look at this split time here, where you have outboard earthquakes, you have large split time up to 3 seconds. Where there are no outboard earthquakes, basically there is no birefringence. And here it just shows some data. The two components are separated in this region, but down here they are exactly in phase. If you look at the P and S wave speed, they show a very interesting pattern. Here I just show the result for P, but S wave basically does the same thing. In the region where you have outboard earthquakes, there is actually not much of an anomaly to speak of. It hovers between 0 and 1%. But immediately south of the outboard earthquake region, you have very large anomaly, up to 3%. And the transition is very sharp. It's about 25 kilometers or so. Then this anomaly sort of peters away as we go southward and eventually fades into the background. This is actually very surprising because if we have earthquakes, we should expect low temperature, which should raise the speed of both P and S waves. But we don't see that at all when we have outboard earthquakes. Now, this is not just another assumption. It's well established that seismicity requires low temperature because the global pattern of deep seismicity is always associated with zone of recent convergence. Also, from experimental rock mechanics, we know that at high temperatures, rocks are just too weak to accumulate stress, which is needed to generate earthquakes. In fact, in a different tectonic setting, intraplate earthquakes in the interior of oceanic plates, they tell us that the limiting temperature in the mantle under near-surface conditions is about 700 plus minus 100 degrees centigrade or so. So now we have a problem because we have earthquakes, yet we don't have high P and S wave speeds. And the only solution is that we need something to counteract this effect. This something is a petrologic effect. Now, the diagram here is just a 3-dimensional rendition based on the seismicity in this region. Now, I mentioned how sharp the transition is from anisotropic to isotropic regions and from no anomaly in VP and VS to very high 3% anomaly here. This is certainly consistent with the interpretation that this cannot be simply a thermal effect. It has to be a petrologic effect at play here. So basically, in the coldest core of this region, we have this petrologic anomaly. Then on the fringes, the temperature rose a little bit. The petrological anomaly turns off, but the thermal anomaly is still there. So we see it in VP and VS. But then, of course, eventually the thermal anomaly peters away from the center of this petrologic anomaly. Well, so far I've danced around calling this petrologic anomaly, but what is it really? Well, to answer this question, you have to endure through this rather long matrix of things. I listed some candidates: metastable olivine, the dense hydrous magnesium silicates, and also the nominally anhydrous minerals, and even including partial melts. Over here are the criteria that have to be satisfied by the successful candidate. I won't go through everything in detail, but say look at availability. Generally, it's not a problem, but the DHMS and the NAM, actually, they're competing with each other. In order for the DHMS to be stable, the surrounding material, which has the same chemical composition as olivine, has to be saturated with water. We need a trigger for deep focus earthquakes. There are ready mechanisms for that. For metastable olivines called transformational faulting, and Harry did a lot of work on that, and as well as Steve Kirby. Now, for these hydrous phases to participate in earthquakes, there is no mechanism. It's called dehydration and embrittlement. But we do need dehydration. You can't just keep the water there. It has to get out in order to produce earthquakes. And partial melt presumably can do the same thing. Also, the earthquake distribution is very specific. We know in several places that the deep focus earthquakes occur on two subparallel planes separated by a few tens of kilometers. And for metastable olivine, this works really well because you expect the transformation to occur on the boundary of this wedge of metastable olivine, which is the coldest core of the slab. For the other candidates, there is no known way of producing the double seismic zone. We need 3% reduction in P wave speed. Metastable olivine can do that if 60% of the olivine polymorphs are in alpha phase. Olivine is roughly 50% of the oceanic mantle subducted slab, so we're talking about 1/3 of the slab being in metastable olivine. And depending on how much water you want to put in these hydrous phases, you can do it. Partial melt can do it. But notice that these nominally anhydrous minerals doesn't produce a lot of reduction in the P wave speed. We need 3% reduction in S wave speed. Metastable olivine can do it. These hydrous phases can do it. But the melt, probably not, because it has a very large effect on shear wave speeds. The shear wave splitting here is plausible for metastable olivine because we know that the oceanic lithosphere has very strong fossil fabric inherited from the mid-ocean ridge. Phase D is very anisotropic, but these nominally anhydrous minerals typically have very minor effect on anisotropy. Partial melt, potentially you could do it, but it's through a different mechanism, not lattice-preferred orientation, but shape-preferred orientation. For this, though, you need a regional stress to line up these melt pockets, basically. And that turns out to be a big problem because there are no patterns in focal mechanisms in the outboard earthquake regions. Metastable olivine has a very specific mechanism for that. It's called anti-crack, and it's a localized self-stress. We need localized source of stress for these hydrous phases to work. The last bit is kind of interesting. It's a buoyancy. If you have that much metastable olivine in the slab becomes buoyant. Well, but this is a self-limiting process. This buoyancy occurs only in the transition zone, but not above or below it. The hydrous phases, on the other hand, would be quite buoyant, and you can't deliver it because it's buoyant in the upper mantle. Now, the nominally anhydrous minerals, the effect on buoyancy is small. And partial melt, the effect could be small depending on the compressibility of the melts. So if you look at this table, metastable olivine is really the only candidate that does not run into a red light here. There are other cases where metastable olivine has been reported. Let me focus on this particular case in isobonin. This was really pioneering work done by Idaka and his colleagues. This is the earliest and perhaps the best example. What they did was very clever. They established that there's not only a low-speed anomaly associated with these earthquakes, there is a double seismic zone. they observed conversion of S waves to P waves across an interface somewhere around here. It doesn't really matter what that is. It's just a reference point. So if the earthquake here and there's a station here, the P wave goes like this. Then it sends an S wave. The S wave hit this interface and sends another P wave there. So in addition to this direct P wave, there's another phase following it. It's this S to P conversion. And the time difference between the two phases is a measure of the distance between the interface and where the earthquakes are. And that's how they can locate these earthquakes very precisely. And more recently, people have reported metastable olivine in the Marianas and also in the Hongshu slab. So if you put it together, we already covered Hongshu, the Izuboni in the Marianas, and the Tonga Fiji region. These are all the regions where deep earthquakes occur, and the instrumentation is good enough to give us detailed results. So now I'm going to move very quickly to the other side of the Pacific, because the configuration of subduction zones there are peculiar. They have subhorizontal orientations, which turns out to be very important in understanding the stress orientations. So here's a map. These colored dots are the epicenters of deep focus earthquakes, but they're color-coded according to their depths. Ignore these large circles. They are not important for this purpose. Over here, I just showed 2 cross-sections, and 3 is this one over here. You see a modest dip of the Valachi-Benioff zone, and the conventional plotting here is the same as what I showed earlier for Tonga, Fiji. Okay, so you can see the t-axis, axis of maximum extension, line up very, very nicely along the dip of the slab. The red ones are the exceptions. There are a few exceptions, but by and large, we have a very close concentration over here. So this is a classic down dip extension pattern. You move to N2 is this bit over here. The slab is basically subhorizontal, maybe has a dip of 3 degrees or so, then it's all red. There is no pattern over here. So we did a global study, and the results are summarized over here. This is basically the dip of the slab. Over here is the deviation of the P or the T axis away from the tip of the slab. We're plotting the standard deviation of the Fisher distribution of sphere. So these places where the slab dip is greater than 20 degrees is your classic down dip extension or compression, because the standard deviation is only about 15 degrees or so. But if the dip is too small, then the standard deviation jumps by almost a factor of 2 to about 28 degrees or so. So the available slab pool is the sine of 20 degrees. That's the cutoff here. That's about 1/3. So it seems like we need about 1/3 of available slab pool to organize the fourth plane solutions such that you will have the classic down dip extension or compression pattern. So the conclusion here is really that localized self-stress is both necessary and sufficient for generating deep earthquakes. Well, how does this really work? Look, there are a lot of earthquakes, some very large, in subhorizontal slabs, and there is no regional stress to speak of. But we still need stress to cause earthquakes. And what else is there? There has to be a local source of stress. No stress is not an option. So far, the take-home message is that we see a very large detached remnant of slab, which is juxtaposed over the classic Valachi-Benioff zone. And we also made a strong case for the existence of metastable olivine. This detached remnant is where the slab went. This basically alleviates this problem of mass imbalance, but it would impede chemical mixing across the 660. So we talk about the Valachi-Benioff zone. We talk about this imbricate slab, if you like. How are they connected? And our contention is that they're connected through this deflected slab, this toe, if you like. The reason being that the toe and the detached slab basically have the same properties. They have subhorizontal seismicity. There is no pattern in the seismic strain. And they have very strong petrologic and petrofabric anomalies. I'm just going to show you one slide for the toe. Again, seismic isotropy. Deep earthquake here, this is basically the toe defined by the distribution of hypocenters shown as these crosses. Again, 3 rays. The AB ray goes smack through the middle of the toe, and it shows very large splitting time. The CD ray, which basically goes down into the lower mantle and didn't touch the toe at all, well, it shows no splitting. Okay? So basically, it's the same as the detached slab. Now, finally, I just want to show another example of the aseismic slab. Now the temperature has warmed sufficiently. The metastate of olivine has all transformed. There are no earthquakes, no anisotropy, but we still have a remnant thermal anomaly. So we will see a modest signature in high VP and VS. And indeed, this northern Philippine Sea anomaly, which is associated with the isobonin subduction zone, it doesn't show any shear wave splitting. It has a modest increase in VP and VS of about 1.5%, or a half of what we observed south of the outboard earthquakes in Tonga. And it's cold, it's dense, it's sitting on top of the 660, and this draws upon there's some very nice work done by Japanese colleagues such as Hitoshi Kawakatsu and Seno. Now, lately, we realized that there is a completely different category of seismic anomalies, and for this, we go to Tibet. Tibet is a very unique feature on the Earth. It's very tall. Elevation is about 5 kilometers. It's very large. It's larger than the state of Texas. There is a consensus that Tibet is built through the collision of India and Eurasia. There's actually a series of collisions. The last episode started about 55 million years ago. It's really the collision of the Indian Shield with the southern Tibet block. It's known as the Lhasa block. And the suture zone is the Indus-Tembo suture right over here. An earlier event in the Mesozoic is the collision of this Lhasa block with another block in central Tibet called the Changtang terrain. And the suture is called the Bangong-Nujiang suture, which is the low over here. There are earlier events, and we are not going to talk about that today. So what we want to do first is to understand the current configuration of the colliding lithosphere. And for this purpose, actually, we had a large-scale deployment supported by the Continental Dynamics program. It's called High Climb, deployed over 200 broadband stations, both a linear array and a regional array shown over here. The result shown here is the so-called finite frequency multi-scale tomography. Hong Su-Hui really did most of this work here. She's the founding mother of this banana donut kernel, and recently she has developed a new method. It's a data adaptive scheme of inquiring the data. So look at this cross-section. It's very schematic. You have a few seismic stations here. You have teleseismic arrivals following these rays here. There are regions where you don't have many rays, and in fact, they don't cross. Then we say, well, let's make the mesh very coarse because we can't resolve any details. In regions here, there are lots of rays, and they cross each other. Then we make the mesh very fine so we can resolve all the details. It's data adaptive in a sense that it just says, look, give me the longest wavelength feature you can resolve. And this is shown over the cross-section here for VP and for VS. Well, what do you see? It's fast in the south and slow in the north. S-wave shows the same thing. So, well, then give me more detail. Then you go down these levels. As you put in more detail, the misfit to the data goes down. And when you get to here, you see a lot of details. You see all these nice anomalies in the crust, which are associated with known rifts here. But for the upper mantle, the most important feature is really this thing. This is interpreted to be the subhorizontal advancing Indian mantle lithosphere, and its edge is now over here, the so-called Indian mantle front. And even if you don't look at the details, you know, at level 1, this feature began to emerge already. Just quickly showed the result on regional view. Just look at the depths at 150 kilometers, and you can see the Indian mantle front right here. And this is the subhorizontal advancing Indian mantle lithosphere. All right, this story is supported by a number of other independent data. We're just concerned with the Indian mantle front here. So down here is the schematic showing the Indian mantle front over here. There are other data. There is earlier work in the late 90s by the MIT group. They modeled the Bouguer anomaly and using plate flexure models. What's shown here are the shear wave by refringence. Here we're using a different type of shear wave. This is so-called SKS phase. It comes through the core mantle boundary almost vertically up underneath the stations. And we are just concerned about the magnitude of shear wave splitting. These are in split time in seconds. So cross-section south to north. What you see near the position of the Indian mantle front, determined from tomography, is this jump in shear wave by refringence. And this is now observed over a large lateral or east-west dimension. This is high climb data collected by us. This is in-depth 3 data. This is earlier data that Serdar Ozalevi and myself compiled. So this is a well-known feature now. We'll talk more about this detached slab a little bit later, but I already showed you the evidence at the very beginning of the talk over this 1,000-kilometer wide broadband seismic profile where the 660 is very small. That's basically the evidence for it. What I do want to say is that the amount of this anomaly, the spatial extent of this anomaly, is actually much bigger than what we've shown here. We are limited by the availability of data. So this is a minimum estimate over here. Anyway, everything up to this point is about space. Right? We do have constraint on timing because northern Tibet over here, there's a thermal event. There are volcanic rocks that dates back to about 15 million years. And so that's the onset of the last episode of magmatism. So we have space, we have time. What is the ratio between distance and time? It's the speed of ground motion. Well, we have that too. There are lots of GPS data in and around Tibet. This paper is about 5 years old. Now there's probably twice as many data as shown here. But anyway, the point is that if you look at the cross-section, okay, this is south, that's north. This is ground speed in the north-south direction. You see a very nice linear trend across Tibet. And I made a circle here. This station is right here, Gaize. This is on the Bangong-Nujiang suture of the southern boundary of the Changtang terrain here. So this is real data along our seismic profile during project High Climb. And we have a lot of data on the northern edge of India, so we know how fast these things move on the surface. And this allows us to do a reconstruction. This is this schematic cross-section again. Pay attention to the Indian mantle front here, and the Bangong-Nujiang suture of the southern edge of the Changtang terrain here. The Lhasa terrain is over here, the Himalayas here. Okay? Now, if we extrapolate backwards using the GPS data, in the Indian mantle front should move backwards or southwards by almost 400 kilometers over 15 million years. So it should move to here. The Bangong-Nujiang suture moves a lot slower, again based on GPS data. It should move back about 150 kilometers or so. But remarkably, those two reconstructed positions are almost exactly at the same place. Now, we want to put this piece back here. We are half successful in the sense that we don't know the exact dimension of this, but there's certainly more than enough space here between this point and that point to put this chunk back there. So let me run the movie forward for you now. Between 30 and 15 million years ago, the Indian lithosphere advanced already past the Lhasa terrain. This is the reconstructed configuration. The Lhasa terrain was over here. And at about 15 million years, the Indian mantle front impinges upon the southern edge of the Changtang terrain defined by the Bangong-Nujiang suture here. And at this point, convection should kick in and remove this thickened chunk of the lithosphere. How does this work? Well, look at the thermal Rayleigh number, which really controls the convective instability of the boundary layer. It has several terms: gravitational acceleration, G, thermal expansion, alpha, delta T is the temperature difference across the boundary layer. H is the thickness of the boundary layer. Kappa is thermal diffusivity. Mu is kinematic viscosity. All these are linear terms except the thickness, which goes to the third power. So if you thicken lithosphere, it becomes very, very unstable, and it will drop off. Now, what happens when the thing drops off? It allows hot material to come in, and this presumably is responsible for the last episode of flare-up, which started about 15 million years ago. Also, this material moves down. It made way for the Indian mantle lithosphere to continue plowing under the Bangong-Nujiang suture until it reaches the present configuration. And right now, this detached piece is sitting on top of the 660. So we first came up with this idea by looking at the P-wave data, and it's natural to look at the S-wave data. You perhaps expect to see the same thing because the amount of temperature anomaly that we expect is about minus 200 to 300 K. We expect the VS to be raised by about 1.5% if it's a purely thermal anomaly. But we couldn't find it. We couldn't see it. S-wave couldn't see this anomaly at all. Well, once again, in order to reconcile the difference, we need another petrological anomaly, which has to counteract the effect of low temperature for the S-wave. But it couldn't touch the P-wave. So what can this be? Well, here we appeal to hydroxyl in nominally anhydrous minerals. This is very nice data, first published by Steve Jacobson and Joe Smith. Basically, they did an experiment of iron-bearing ringwoodite with 1 weight % of water. So they show the result for P and for S. Look at the S-wave situation. 1% of water will decrease the VS by about 3%, and this effect is expected throughout the depths between, say, 250 and 750 kilometers or so. For the P wave, initially there is a reduction, but the reduction disappears as you go to the depths of the transition zone, because not only the hydroxyls change the values of VP and VP, it also changed the pressure dependence of VP. So by the time you get to the transition zone, the effect is minimal for VP, but for VS, it's a different story. So let me show you a little table how this really works. There's VP, there's VS. You have low temperature, both should increase. But if there are hydroxyls, it leaves VP alone, but it will reduce VS. So you add the effect together, you will see an anomaly in VP. You will not see an anomaly in VS. Now, in the mineral physics community, there is still some argument as to what the exact values are for this reduction and so on and so forth. But I should emphasize that having some iron in ringwoodite is really important. If we look at the magnesium, pure magnesium system, you get an answer which is probably not realistic. Well, I hope you're absolutely convinced about this interpretation. If not, there's some supporting evidence for this. Before thickening of the lithosphere, the Changtang terrain was part of a mantle wedge. And we know modern mantle wedges are very wet. And this is some nice data from different island arcs. And you can have several weight percent easily in those volcanic rocks. And the partition coefficient of water between melt and the source is about 10 to 1. So if you have several percent of water in the volcanic rocks, you can have something like 0.5% of water still in the source region. More directly, if there are many samples from these volcanic rocks in Tibet, and those samples contain phlogopite, which is a hydrous mineral. So again, those rocks have a lot of water, and they came from a source region that still has a lot of water. Okay? Now, when you think about this is quite interesting, because during contractional tectonics, when you thicken something, we're basically advecting cold material to depth. And we know that rheology has a very strong dependence on temperature. So if the temperature goes down, the deformations will stop. So as soon as we thicken the lithosphere, it wouldn't want to thicken anymore. However, hydroxyls would facilitate continued deformation. So this works out quite well. Without the hydroxyls, you wouldn't expect thickening of the lithosphere at all. Now, finally, I want to touch upon the issue of deep water cycle. The discovery of water content in those nominally anhydrous minerals is very important, because they can contain so much water such that the mantle can hold a lot more water than all the waters in the current oceans, okay, 2 to 10 times. So we know that there's a very big bucket in the mantle. The question is, do we have any water in this bucket? In order to bring water into the bucket, it has to come somewhere, either from above or from below. The conventional view is perhaps the obvious one, that this pathway, tectonic pathway, is subduction. There is a lot of water coming down with the subduction slab. Well, most of it is near the top of the slab. We don't know quite well how deep the hydration goes. In the meantime, there is dehydration. As the slab comes down, it gets heats up. There is a lot of dehydration. We also don't quite know exactly how much water remains in the slab. But here we have an alternative. During continental collision, we have this convective removal of thickened lithosphere, which contains a lot of hydroxyl because it was part of the mantle wedge. And that's very nice. You don't have any stability problems, because olivine can hold a lot of water, up to 1 weight percent. And when it enters the transition zone, Volatiles can hold up to 3%, ringwood dye 2%. So you would not expect dehydration. Now, turns out there's sort of theoretical support of this idea. Elkins and Tannen actually invoked the same idea to study the early history of the Earth. And recently, Harry, Mike Brzezinski, and I published a paper together arguing that based on the distribution of default focus earthquakes, dehydration cannot account for these observations, and therefore the slab probably is not a very effective way of bringing water into the deep mantle. So the story I'm trying to tell here is actually very simple. The key is that we have to recognize there are two different sources of bringing cold material into the transition zone. Let's start with the simple one. This is a continental collision, convective removal, hydroxyl-rich material here. Metastable olivine and hydroxyls don't mix. If you have more than about 100 ppm of hydroxyls, metastable olivine will just turn into spinel. There's nothing left there. So here you would have an aseismic remnant, like what we see in Tibet, but you will see a discordant anomaly. It's detectable only through P waves. S wave won't see it. The other source is the obvious one, is the subduction. Here, you don't bring that much water into the transition zone. Then you will have deep focus earthquakes associated with these anomalies. You will have strong shear wave splitting. You won't have high VP or VS because metastable olivine has low VP and VS. Now, there is this evolution path going from a seismogenic anomaly to an aseismic anomaly, which would show concordant VP and VS anomaly, but no splitting, no earthquakes. Then eventually the thing is assimilated into the background and nothing. That is the complication. And this is the part that we spend a lot of time on, talking about how a Volatiles zone goes into a deflected toe and then eventually evolved into this seismic remnant, which is buoyant. Therefore, it doesn't go into the lower mantle. And eventually, it evolved into the aseismic remnant over here. So the overall story, I believe, is actually quite simple. Right, I just want to put this picture up here. When Birch published his paper, he did not have the help of a conceptual framework. That is the framework of plate tectonics. So he couldn't really say too much about the effect of strain rate, thermal convection, and global tectonic history, which turns out to be all very important. Now, in the last 2 decades, we have had the exponential growth of high-resolution seismic data, a lot of new technology. Also, we have cutting-edge tools in experimental rock physics, such as the advanced photon source. And also, there's computational geoscience. Right now, as we speak, there is this petascale computing, 10 to the 15th floating point operations per second, being built. It's called the Blue Waters, being built on the campus of the University of Illinois. And imagine what we can do with the geodynamic computations there. But what's really important, of course, is the paradigm that was set forth by Birch, and with apologies to Thomas Edison, there's aspiration, inspiration, and perspiration. Before I stop, I do like to acknowledge the contribution from several people. Both Mike Barzinski and Tailin Zhen did their PhD thesis on the subject, and Harry Green here has been a source of constant inspiration. And Su-Hui Hong lately has been working with us, providing a lot of new techniques and such. With that, I thank you so much for your attention, and I appreciate the opportunity to speak to you this evening.
We do have plenty of time for discussion. This is the presentation is being taped, and so please ask your questions carefully. That is, speak loudly. And I ask Wang Ping to repeat the questions so that it'll be it can be heard and recorded as well. So I now then call for questions and comments. Except that I can't see you.
Larissa has a question.
Ah, sorry. Thank you.
Thank you very much for this presentation. I have one problem to understand. You mentioned that metastable polymer, even if it is in a very deep environment, doesn't wish to accommodate hydroxyl water because the converter is thinner. So what prevents this dissolution of the water into metastable polymer?
I'm not sure I understand your question completely.
Please repeat the question as best you can.
Why metastable olivine doesn't wish to interact with the water?
Oh, okay. Well, the question is, why doesn't metastable olivine interact with water? I guess it's really a question of the availability of water. In my mind, anyway, most of the metastable olivine came down through a slab. So if the slab wasn't very wet to begin with, and this metastable olivine is in this cold core, then there is no reaction. If you believe that the slab is very wet and there's a lot of water there, then metastable olivine would not exist very long. I don't know if I fully addressed your question. Okay, if the transition zone is already very wet. Okay, in that case, basically, even if you have 2% of water, it's going to be locked into the nominally anhydrous minerals because it's happy there. It doesn't want to get out. It's part of the crystal structure. Maybe there's some experimental data that I'm not aware of, but that would be my reaction. Yeah.
Well, if I may, the slab is going down very, very fast. And so even if there were water in the surrounding transition zone, which there may very well be, it doesn't have an opportunity to react because the slab goes down so fast. Other questions or comments? Sorry, I'm peering, but I've got to keep the light out of
over
my...
there to the...
You're seeing better than I am. Thank you. Over there, please.
This. Okay, I believe the question is that whether the observed isotropy is consistent with the expected orientation of the fabric. Is that correct? Okay. In the case of the Tonga, Fiji region, we did consider this issue, and it is consistent with what you expect if the paleofabric is inherited from mid-ocean ridge. Now, there is a possibility, if I may, go back to perhaps, excuse me, it's going to take a little bit to get there. Okay, here we are. There is a possibility that this is a remnant slab coming from the north, from the Vitias Trench, which shut off about 8 million years ago or so. We can't rule that out because given the reconstruction, that fabric coming from north would also work. Okay? But other than these two possibilities, we're not aware of any proposed direction for us to consider.
Yes, over here, please.
How do you explain the double zone in the upper mantle?
Yes, in the upper mantle, the mechanism, metastable olivine couldn't do anything. There is no metastable olivine much above 410. So it requires a different mechanism. And again, a number of people, including Harry, has done a lot of work there. Basically, it looks like the shape of the double seismic zone in the upper mantle is sort of a very narrow Y shape. It merges. And that follows very nicely with the expected dehydration reaction of basically high temperature serpentine such as antigorite and such. So it does call for a different mechanism.
Yes, over here.
Yes, I believe the question is that if we look at a realistic rock package or take into account some simulations that the metastable olivine wedge may not produce the double seismic zone. I mean, The argument I presented is simply from a thermal standpoint. The pressure overstep is about the same throughout the slab, but in terms of the temperature, the edge of the wedge has the highest temperature, right? So you would expect the reaction to go there first instead of, say, in the middle of the slab and such. We are aware of some calculations and experimental data. For instance, Dave Ruby's group has done a lot of work there. My understanding is that there is some fudge factor that you can play in, like in most models, and also that perhaps we have underestimated the temperature anomaly in a lot of the calculations. There is a way of getting around that. Basically, if you map out the topography of the 660, and we know from laboratory data what the Clapeyron slope should be, then you can back out a temperature out of that. That is actually working in progress, but it's not going to be easy because you need a three-dimensional wave propagation issue to be resolved. And right now, the technique is there, but it's very expensive, very time-consuming. But we are working towards that direction, and that perhaps can provide a way of resolving this issue. I think we're standing between dinner and wine.
Yes, and so on. So let's call it to a close, and thank Wong Ping again for a very stimulating lecture.
Thank you very much.